So let's develop new solver. Okay, so here idea is something like this way. Try to implement CHT multi-region form for incompressible fluid. Okay, so it's going to be a very big I say project or the solver development. Okay, here if you look at the pre-defined or available solver, okay, so let's go to that area. So applications, solver, heat transfer, CHT multi-region form. If you see, okay, so this is a combination of heat conduction and buoyancy driven for conjugate heat transfer between solid zone and fluid zone. Okay, with including the let's say FV options is included. Okay, and buoyant driven solver. So if you look at it, is more like developed for compressible class of the fluids. Okay, so we want to let's say redefine the new solver that will allow us to simulate on a incompressible domain, and let's say we don't want to go towards turbulence, so incompressible laminar domain. Okay, so that means we have to adapt the flow solver from the incompressible side, that is the let's say in transient incompressible solver for laminar application. It's let's say Ico form, so we adapt from the Ico form, and Ico form to piezo or pimple, it's very easy. So let's start the development of entire new solver. Okay, so where idea is very simple. We want to develop a solver that will facilitate us to take into account the concept of incompressibility. Okay, and also it work with the let's say multi-zone type of the cases. Okay, so that is the idea. So what we are aiming is the multi-region heat transfer solver for laminar incompressible flow with some scalar transport equations. Okay, and that is basically we try to develop based on this CHT multi-region form. Okay, so let's first try to add up this solver and then try to modify the solver. Okay, so if you want to develop this CHT multi-region based incompressible type of the solver, let's copy this, okay, into our area. Okay, so here let's paste this, okay, and rename it. So I want to give the name as a Ico CHT multi-region form. Why it is I say Ico? Because we want to adapt based on the Ico form. Okay, Ico CHT multi-region form. So immediately first change the name for .c file. Okay, then later on we start fixing couple of the things. Okay, this simple, let me delete it, make file also let me open. Okay, so if we see, we have a fluid side this CHT multi-region form. I want this way. Okay, and right now I don't want to change any other thing. First let's establish the template so that we able to run it. Later on whatever not needed we try to remove from this option area. So let's say our template is ready. So let me first compile it. Okay, so we want to develop based on this OF 3.0. wclean.all. Okay, so let's develop the first on the template, then we start modifying based on our requirement. Okay, so our template is ready, we able to compile it. Okay, so our template is ready to go. Now let's try to modify it based on our requirement. Okay, so few things first understand about this particular solver. Okay, so if we look at the its detail, okay, detail aspect of this CHT multi-region form. So first let's understand few concept here and then we try to modify it. Okay, so now this is no more CHT, it is Ico CHT, okay, multi-region form. Okay, and this solver if you see, it has a two part. One is for the fluid zone. Okay, so it try to solve couple of equation for fluid zone and try to solve couple of equation for solid zone. That means it is a couple type of solver. Okay, and if you look at the few of the header files, okay, so it is available here. So here fvcfd.h file is a standard finite volume header file. Then rho thermo, basic thermodynamic property based on density, it try to take into account. Then turbulent thermo model.h. okay, so it is defined for RANS and LES modeling, and it give us the idea about the some boundary condition that is available in the turbulent thermo.h file. Okay, then this fixed gradient define the fixed boundary conditions. Okay, regional properties simply hold zonal information. So what is zonal information? Here we have fluid zone and the solid zone, so it give you the idea about the zonal information. Then compressible Courant number calculations. Then solid region Courant number, so it give you the idea about the how to calculate solid zone Courant number. Then solid thermo, okay, so that is fundamental solid thermodynamic property file. Then radiation model, FVIO options enable us to look at the FV options, coordinate system.h files. Okay, so basic class of other coordinate system if you want to look at it, try take into account. Then flux, fixed flux pressure FV page scalar field.h file. Okay, so that is the different class of the boundary condition. If you want to incorporate it, straight away goes inside. Okay, then set root class, and this is and create the time. So set root class is nothing but check for the folder structure, and create time, definitely create the time from the control dict file. Okay, then we have a create fluid mesh and create solid mesh. Okay, so create fluid mesh, definitely create the mesh for fluid domain, create solid mesh for creating the mesh for solid domain, create fluid field. So if we look at the create fluid field file, so for that we have to go toward the fluid area. Okay, so create fluid field. So here we try to establish the all the different zone fluid properties. Okay, so that is what exactly we required for different zone. We try to read the fluid properties depending on the number of zone. So here we initialize in terms of arrays. So row of fluid is not a single value, but is depend on the fluid zone size. If in your domain, if you have 2 fluid, then it has a 2 entry. Through 3 fluid, only 3 entry. Same way for all of these things, we require the number of depending on number of zone, we have to read that files, and here we are reading each and every quantities. Okay, so that is what read create fluid field. In the similar line, if you have want to look at the create solid field, it is available in the solid area. So go to the solid area, we will see create solid field. Same line, based on number of solids zones, we able to create the solid zone. Okay, and then we try to read the solid zone property for each and every solids. Okay, so that is the idea about that part. Okay, then initial continuity error, create time control, read solid time control. Okay, so read solid type control is also available here, read solid time control. Okay, so maximum di. Okay, so that is read the control parameter using the solid solver calculations. Okay, so that is available. Then compressible multi-region Courant number. So that is compressible multi-region Courant number. So how to fix the Courant number for compressible multi-region, it is available here. Okay, so compressible multi-region Courant number calculations available. Then solid region diffusion number .h, so that is available in here. So diffusion number file. So how to calculate the diffusion number for the solid region diffusion number, we try to calculate based on rho Cp and kappa. Kappa is thermal conductivity. So all the information is available in this particular place. Okay, Then we have a set initial multi-region delta t, so we fix the delta t for multi-region type of the things. Then create time control, read solid control, read pimple control. Then within each time loop we going to read this, okay. And then we start for let's say store old fluid.h file. So and here exactly we are starting the pimple loop, okay. So here what we say is that the number of fluid zone and number of solid zone, we try to solve this number of equations, okay. So set region fluid, then read multi-region pimple control and solve for fluid. So solve for fluid is exactly the solver for fluid side. So solve for fluid, if you look at, okay, we have a this if it is a frozen zone, then only solve for this energy equations, okay. Otherwise it go for regular route and try to first solve for rho equation, then u, then e, energy equation, then the pressure equations, okay. And like that way we can fix the solve for a fluid. In the similar line for solid part also, we say that set for region solid fluid.h file, then read solid multi-region pimple control.h and solve solid.h file, okay. So that many things we have available here, okay. So this is the normal structure of this particular solver. So idea is that whatever the available in terms of the compressible class of the things, we try to change in terms of the incompressible class of the things, okay. And appropriately we try to modify appropriate files, add new files, delete new available existing files, and appropriately we try to change such a way that we establish a Ico form based simple multi-region class of the solver for a scalar transport inbuilt, okay. So that is the idea. So let's try to explore in this regard. So let's start modifying this particular solver, okay. So if we want to modify, let me first open the Ico form, so it gives us the idea what exactly change required, okay. So incompressible Ico form, let me open this Ico form file. So if you look at the Ico form area, okay, so in the Ico form we have FV, then piezo control we required, okay, and few more things we required, like U equations, okay, something like this way, then P equations, okay. So appropriately we have to change these equations as at a proper locations, okay. So that is the idea. So now let's try to modify this multi-region form, okay. So multi-region form, if we look at, we are developing for incompressible class of applications, so definitely it is better to change this heading. So combination of heat conduction and buoyancy for conjugate heat transfer, no more there, okay. It is for it is a multi-zone heat transfer solver, so it is a multi-zone basically, okay. It is a multi-zone heat transfer solver, okay. That is in fluid equation is in laminar in nature, fluid is laminar incompressible, okay. Laminar fluid is laminar, and scalar transport we have to solve. Scalar transport scalar transport of, let's say, temperature is solved, okay. Scalar transport of is solved, okay. So that is very simple definition we want to incorporate. So let's try to develop this solver, okay. So idea is very simple. So now whatever is not needed, first comment it. So rho thermo not needed, this is not needed, okay, at present. Fluid fixed gradient FV patch field dot h file needed, okay. Then in case, okay, so if you want to generalize in terms of, let's say, even for this piezo or pimple class of applications, so it is very easy to extend. So I am adding few lines from this area, okay, even though right now it's not going to be needed, okay. So what is needed is we added this new line, single phase transport model dot h and turbulent transport model dot h files. Then we have a zonal property, okay. We don't require compressible Coron number, but in case of the compressible we required, let's say, new compressible, incompressible Coron number, okay. Then solid, this required. Now no more solid thermo required, radiation not required, FV option we not going to enable, coordinate we not enable, okay. Then fixed gradient pressure not required, okay. So these all the things at present I am commenting. If we required, we again keep it on, okay. So very simple, no worry, okay. Now set root case, create time definitely required. Then RP, fine. Create fluid mesh dot h file, and this is required, okay. Create fluid mesh, create solid mesh, then create fluid field, solid field, okay. Continuity definitely be required, okay. Then create time control dot h, read time control dot h file, let it be. In case of this compressible multi-region Coron number, we try to fix it as a incompressible or Ico multi-region, this thing. Then solid region diffusion number dot h file, and set initial multi-region property. So I am not changing anything, okay. So wherever, so this is I modified, okay. So I am keeping wherever I added anything, okay. So we have an idea that this is what we added. Let's say added, okay. Same way this is added and this is we modified, okay. So we at least know that whatever is modified and whatever we added new, okay. So this thing we added, this is the modified one, okay. Rest thing we commented. So any other things from this side, so runtime we start from here. Then we have a create time control, okay. Read solid time control, fine. Read people control, no problem. Then same way, in case of compressible we required Ico multi-region Coron number, so that is what we modified here, okay. Then solid region diffusion and this multi-region, so let it be like the same way, okay. Then time will going to start from this, okay. So after the time start, we can check for fluid region and store old field.h file, okay. So that is fine, let it be. At present no need to change. Then we say that set regional fluid field.h, then read multi-region pimple, solve for fluid, okay. Set region solid fluid, read no change, any change required, okay. So as far as this main file is concerned, we are set for a couple of the things, okay. But if you compile right away, it's going to give you the error because we modify so many things, okay. Now let's try to establish step by step all the required files that is needed for the calculation. So first part, if you see, okay, so this is very important. Create fluid field .h and create solid field .h file, okay. So let's first modify these two files. That is where we exactly defining the new variables, okay. So that is very important place. So let first define that at appropriate locations, okay. So fluid let's say create fluid field.h files. Okay, so create fluid field.h files. So at present we have a row thermo. So in case of the row thermo, we have to change row thermo to the single phase transport model. Okay, so let's see if any place we have that entry. So go to the create field.h file. Okay, so we have this single phase transport model dot this file. Okay, so we have to adapt this single phase transport from here. So adapting from where pimple area. Okay, so in case of the row thermo, now we don't require anything from the row thermo. We have to adapt this from the single phase transport model. Okay, single phase transport, and let it be a row thermo region fluid. Okay, so that is what change I did here. Okay, so thermo fluid, that is the name we define. Okay, and exactly the same line like laminar transport, in the similar line we define the name as a thermo fluid, and fluid region dot this give us the size of the number of fluid domain and number of the solid domain. Okay, now what else we needed? We require the properties. So row no more required because we are working with incompressible part, so this is commented. Fluid definitely required, then phi of fluid required, then G and H, rho G, this all quantities not required. Okay, so whatever not required, let me comment. So now we don't require G, that is we don't require HREF fluid, we don't require GHF. Okay, GHF fluid also not required, let me comment. Then we have a later on we fix about this turbulence model, but before that what is needed? We required definitely the scalar field. Okay, that is this, from this scalar field let me add up few more things. So along with that, what is needed? We required pressure. Okay, so in case of the P row, we require the P of a fluid. Okay, pressure of a fluid, as well as we want to define the temperature, so we say temperature of a fluid. Okay, and when we defining the temperature, so for each zone we have to define the K, that is thermal conductivity of a fluid. Okay, K, then also few more thing we required. Okay, that is some constants. Okay, so why that constant is needed? So if you look at here, okay, so we in the incompressible domain we normally read this nu PR PRT, so all that quantities, if we talk about the temperature, okay, so we require this nu PR and PRT as a some dimensional dimension scalar, we have to read that. Okay, so from where we add up that, so let's go to the again solver, heat transfer, let's say bind pimple form, create field. Okay, so dimension scalar we required, so I'm adapting this quantity as a dimension scalar from here. Okay, so let me copy this one more line. Okay, so here what we needed some dimension scalars. Okay, so in we adapting this dimension scalar from this area, so we said that dimension scalar and dimension scalar in terms of nu fluid. Okay, so that is one. What else we needed? We required let's say Prandtl number, that is normally we use for energy when we have energy equation, and turbulent Prandtl number. So that is the three things we normally required. Okay, so we adapted that thing. So then we required this turbulence model, so let's add up that turbulence model. So in case of at present we have a compressible turbulence model, so look at here, we in case of this we require the incompressible turbulence model. So let's add up this incompressible turbulence model from this area. In case of this, in case of incompressible, now we have incompressible turbulence model. Okay, turbulence region, that is fine. Then if you look at here, we require some reference pressures and reference cell value. So we require pre-reference cell and the sum. So this is as a label and this is as a scalar. So in the similar line, let's add up this as well. Okay, so these two things we required. So let's copy this. Okay, Control V. So this is called a label. In case of dimension, this is label, and label for what? P reference cell. Okay, so let's write it down. PR, in case of PRT, we say P reference cell for fluid, that is goes as a label. Other things needed is the scalar. So let's, in case of this, we require P reference value. So we are adopting that as well. So we are set with this as well. Okay, so we are set with all the properties. All these other properties no more needed. Okay, so let me comment till here. Okay, so this is based on incompressible part. So whatever is needed, we are adapting that. So let me copy from here to here, and also at a time commenting. Okay, so this is all commented, so we remove that, and this is what we needed, that many things. Okay, so that many things we needed. So whatever we adapted new, we try to code it as well. Okay, now we're reading the fluid mesh thermophysical property for region, and it give you the name of region, adding the what we want to add here. We want to add, let's say, K of a fluid. Okay, so K of a fluid is a scalar quantity. Okay, so here we don't have to add this thermophysical set value. Okay, because that is not the part of our area. So what we are adding, even this is also not the part of this area. Okay, so whatever not needed, we try to comment out. But first thing, what is needed, we needed the U files. Okay, so let me arrange in similar fashions whatever we needed. So let's say U file we needed first. Okay, so let's start with here. So we add the U. Okay, so first one is U, then we require phi, rho phi. Okay, so rho phi is here, so let add up that as well. So rho phi. Okay, so then we require pressure. So pressure we try to add up as a scalar. So let's modify it based on this. So I don't want to modify there, so better try to select P fluid. Okay, in case of this, it's a P fluid. I scalar object is a pressure of a fluid. Okay, so P fluid and P fluid, but we don't want to use this rho thermo. We say for the zonal I. Okay, so we say P fluid, but for the region I. That is what we needed. So we have a P fluid, then we have a T fluid. Okay, so P fluid is done. After that we require the temperature. So let's say adding the T fluid, set for T fluid, then rho fluid, T fluid, then K fluid. Okay, so let's add up the K fluid as well. So let me add up from here itself. What is needed, we require the K of a fluid. Let's say K of a fluid, object is K of a fluid. Okay, but all these things we have to read. Okay, so we say must read, we cannot skip that. Okay, pressure we must read. Okay, and auto write definitely. Similar, and temperature also must read, auto write. K also must read and auto write. Okay, so we set with K, T, rho. Now we have to add up few more things, like adding this PR and all that entries. Okay, so adding thermophysical properties. Okay, so adding thermophysical properties, so like the way we are adding here, but we have to add with different way. Okay, so after K, let me add up here. So let's say we want to add up the thermophysical properties. So adding thermophysical property, that is correct. Okay, but that thermophysical property we have to add up not like rho thermo, but we have to add up this thermophysical property based on something like this way. Okay, so thermophysical property, if you see, okay, so how we are adapting here in the similar line, we try to adapt. Okay, for this, so we say it is creating the based on single phase transport model, laminar transport. Okay, so that is the name for that particular case. So appropriately we have to modify it. So we say that it is not a rho thermo, it is, but it is a we say it is a something like a single phase transport base. So fluid thermoset, so we say single phase. In case of the rho thermo, we say that it is a single phase transport. Okay, so PTR thermofluid and regional, that is fine. Okay, so we have to adapt it from here. Maybe it will give us certain errors, but no worry, later on we refine. Okay, so let's say this is a single phase transport model. Okay, and we are constructing a new single phase transport model, and based on this property, if you see, so that single phase transport model is constructed based on U and phi. Okay, so let's say U for which, U for the zone, but now no more we have a U. Okay, it is no more U, it is name is U fluid. Okay, so in case of this we have a U fluid and zone 1. Same way it is no more phi or phi, it is a rho phi. Okay, so its name is no more as a phi, but it is name is a rho phi, rho of a phi of a fluid. Okay, so that is what we're going to use here, and the zonal entry. Okay, so this is how we adapted that part. Okay, now with this what we want to also add the turbulence model. Okay, so if we look at here how we added the turbulence model, so just we add the thermophysical property. Okay, then let's see how we add the turbulence model, like here, look. Okay, so let me first copy this area near to our area where we are started the modifications. So let me keep a line, so we know that this is before this line we are modifying everything, and how we want in this area, just check that. Okay, so this is till now we have. Okay, so in case of this we said add turbulent set, it fine. Here we required incompressible turbulent. Okay, incompressible turbulent and new. Here rho no more required. Okay, we required U fluid, flip few, fine. PTR, okay, I think that's fine. So with this we able to add a U, phi and thermofluid. So what is thermofluid? Thermofluid is nothing but whatever we set here. Okay, so thermofluid is give you the idea about the from, if you check from here, laminar transport. Okay, so let look at this laminar transport is nothing but the this entry is combined. So let's check here it's went properly or not. So if you see what we have, from the single phase transport we create the laminar transport, and for the turbulence we use that laminar transport. Same way from here single phase we use this, okay, as a new fluid, this new single phase transport I, okay, and from that we try to adapt this entry. So that is I think fine. So we added that entry. Okay, now what we require, we have to set the values. Okay, so how to set the values? So normally we set this cell reference values. So just check that value how we are able to set here. Okay, so set values we require. So let's see anything related to set values we have here, then we able to add up that. Okay, this set values we have, I think we don't have, no worry, but we construct set values. So that is the what we needed. So let's construct that set value. Set value, okay, and inside the set value whatever we needed we try to modify it. Okay, so inside the set value what value we have to set? We have to set for pressure. Okay, then we supposed to add up this control directory, then reference fluid, and all these four things we have to add up. Okay, so let's copy first this four part. One is pressure, okay, then some pimple directory, then this reference value, and this thing. So P is no more P, it is we have a P fluid, and the same things it's supposed to go. Okay, so P fluid, then reference cell fluid and reference value. Now the problem is this pimple dict file, how to resolve that. Okay, so we require pimple property. Okay, so let's see anywhere they set this value here, pimple K thermophysical. Okay, so pimple dictionary they set something like this way. So let's copy into near to our area. Okay, so what they did that pimple dict, that is what we want to set here, is nothing but fluid zone dictionary sub dictionary. So that is the line we needed, that's it. So in case of pimple dict, that is the line we required, the fluid region first, solid dict file subdict pimple, and we set for this reference value. Okay, so that is what we needed. So we set with that reference values and all these things. Now what else needed? We have to fix for all these numbers. Okay, so we have to read the Prandtl number. Okay, PR, and PR we supposed to look from the thermophysical properties. Okay, PR new, PR and PRT, that three numbers we supposed to read. Okay, so let's see how they are reading here some values. So P or K, they set K, they are not reading from thermophysical property, any thermophysical property they are not reading. Fine, so let me check where something is read based on the thermophysical property. So easy part is, let's look at the basic solver, scalar transport create field. So something we read based on this thermophysical property. Okay, so let's add a few things from here in our area. So we have to read what we have to read for new PR and all these things. Okay, so definitely the set command is required. Okay, so this is normally we are using. Okay, so we say that in case of this we say, let's say NU and fluid, new fluid set. Okay, for that what is needed, we require this bracket. Okay, in this it is definitely a new. Okay, so definitely we required this entry here. It's not mu, it is new, nu. Okay, new. Then whenever we want to define this like this way, okay, so new, I think it is perfectly all right. In similar line we able to read it. Okay, so new, but what is new now? We have a what is that quantity? It is a dimension scalar. Okay, 5 minutes. It is a dimension scalar, so we say that it is a dimension scalar, and we going to look for how we going to read. So it is depend on thermophysical property dot look. Now we don't have a thermophysical this transport property. In case of the transport property, what we have is this thermofluid file. Okay, so here in case of this we have a thermofluid file. So let me define, let's say thermofluid. This inside of it we have to look for this entry. Inside of it we have to look for this entry, and we say entry name as a nu. Okay, so with the help of that we able to read this file. I hope it will work. So new is set. Okay, now in the similar line we have to set for PR. Okay, so let's say PR of fluid. So and we say that PR here. Then another is PRT. What we use capital PR and capital PRT. So we have to work with the same way. Let it be capital here as well. New we say PRT. Okay, so we set with, I think, all the reading part. This is not needed, I think, up to end. Okay, up to the last bracket we able to comment it. This belong to this, fine. So zonal property we are set, I hope. Okay, so fluid, create fluid part is almost done. Okay, so now idea is that how to set a similar class of properties for solid side. So let's try to explore that as well. Okay, so create solid field .h file. Okay, so let's open that from the solid area. So create solid field.h file. Okay, so create solid field.h file. Now coordinate we don't require. Solid thermo. Okay, so no more we have a solid thermo, forget that part. Radiation model not required. FV options not required. Okay, what is needed? We require certain entries like rho of solid, CP of solid, then K, that is kappa or conductivity of solid, and the temperature of solid. Okay, so that is what we needed. So let's see. So I think not required, not required, not required. So what is needed? We needed some of these entries straight away. Okay, so we say that PTR. Okay, so if it is here, in case of fluid, now we have a this, and here first of all definitely we require the volume scalar field as a temperature, and in case of this let's say TS, so solid temperature. Okay, first thing. Then we required its rho of a solid. Okay, then we required, let's say, CP of a solid, then rho CP, as a combination, sometime it goes. Okay, so rho CPs. Okay, then last part needed is the K, thermal conductivity. Okay, this is not needed, so let me kept it here. Okay, so this is all commented, okay, from the older entry. So we have to read that many thing only, that's it. Okay, so let's start. So reading for thermo property of region 1. Now adding a thermos, so we need not to add any thermo. Okay, so need not to add this thermo or anything. So what I am doing, let me put it something like this way. So before that we try to add. So what we required the temperature as a volume scalar field. So volume scalar field as a temperature we required. Okay, so let's try to add up from this area. So where is volume scalar field? This one. Okay, so let's say start with this, let it be a temperature, yeah, here. Okay, so let's add up this from this side to this side. Okay, so we are adding, okay, here temperature. In case of T S, it is no more T fluid, it is TS, T of a solid we are reading. Okay, TS, new volume scalar. IO object name is, let it be a T only. Okay, temperature, and it goes inside the, in case of here it goes inside the solid zone. That's it. Okay, so we able to read the our TS file, and it is must read and auto write correct. Then we have to read for next one is rho of S. So we say that rho of S we have to read, rho solid must read definitely. Then we have to go for a, here also rho of a solid we are reading. Then we are reading CPS, CP of a solid, set for CPS. Here we say CP must read. Okay, auto write. Then we have a rho CP, rho rho CPS we have. Okay, so rho CP S we have to set as a from the volume scalar field. Okay, and already rho and CP we have, so no need to write it down again. So let's finish this part from this side. It is a volume scalar field. Okay, and name of that scalar field is rho CPS S. Okay, rho CPS, or we say rho S and CPS, that is better. So we say rho S and CPS, that is a I think better name, because rho of a fluid and CP of a fluid. So let me change it here, rho S and CPS. So we read rho CPS, we read. So how to construct is very simple. We have a rho S for zone 1 star, CPS for zone I. That's it. With the help of that we are able to construct the rho CPS. Okay, then last part we have to add is K. Here, rho CP now we have to add this entry about the k kappa ks here we say k, fine, must read, right. So we are set here, and all rest the things we not needed, so simply comment it. Okay, this is still here needed, fine. So we are set with both the create field files. Okay, so create field files we are set. Okay, now so we set with create fluid field and create solid field. So before we go further, okay, so let's say comment from here till here. Okay, so I'm commenting all these parts, so at least be able to check either this create field file is set properly or not. And what we needed, Ico current number files needed. Okay, so that is we have to check Ico current number file. Where is this? So we required compressible current number. In case of the compressible current number, we required the Ico current number file. Okay, so let's see that files. Ico current number, rename it to Ico current number file. Okay, that is what at present we needed. Later on we define it. So in case of this incompressible current number, we says that it is not incompressible current number, it is Ico, this everywhere. Okay, so row 5, I think it's supposed to work. Okay, without any problem. If not work, then we will think how to fix that, but right now let it be. So clean, let's see. Okay, so compressible current number .h file, fluid compressible current number .h, from where it is coming, solid zone, we commented everything correct. Yeah, okay, I'm at the right location, no worry. So create regional property turbulent, fine. So okay, compressible current number, it is asking from file area here. In case of this, we have a Ico current number, and here solid diffusion number, fine. So that is missing, it's saying, no problem. Ico current number .c file, Ico current number .c file, here rename it. Okay, Ico current number .c file. Okay, so this Ico current number file we have to set maybe by some different ways. Okay, so later on maybe we have to fix this Ico current number some different ways. Okay, so later on we try to fix this Ico current number, but right now let it be the similar way. In case of this, we say Control C, Control H, Ico current number, we say that, fine. I think it's okay at present, fine. So let's see. So Ico current number .c file we set, solid region diffusion number .c file we set, Okay, single phase transport.h file is missing. That is correct, because that options we didn't add here. So from the pimple area, let's look at the options here. So we required what? We required the transport models and the single phase transport models. Okay, so transport models and the single phase transport models we required. Compressible later on we removed. So first we check that whatever the create field files we use, then turbulent transport model.h file from the CHT 38.45 turbulent transport model.h file. So that is supposed to be here. That files we add transport model, turbulent transport models, we have to add that file. Fine. So that error we able to remove. Now only things is okay. So let's see. Row fluid. Okay, create fluid field.h file, 83 lines. Create fluid field.h file 83. Okay, so what it says is that not declare in the scope row of a fluid. That is correct, because we are not reading the row of a fluid. We are not reading the row of a fluid. That is correct. So let me check how we able to fix that entry. We required the row fluid, correct, and now we don't have that row, so it is incompressible fluid. So without row only it's supposed to goes as an interpolation. That is perfectly all right. Okay, so because that is fine, that is perfectly all right. Then 168 numbers, 168 numbers, fine. Yeah, this is missing, correct. $170. Okay, row set fluid set reference cell, correct. What is saying? Primary broken. Why it is broken? Didn't get. This is fine. Fluid zone, then solid dict, then subdict, and be able to fetch that value from here. P reference fluid. Oh yeah, correct, because this is not needed at the end. Fine. Sometime very small things as a typo and it shows some different error. Okay, primary broken. Okay, but fine. Now what else we have a problem? Failed. Why? And one exit. Okay, but here compilation of this part, I think no worry, it's set. What about this? It's also set. Let me see the user application Ico CHT, fine. Okay, so then where is the problem? So we are getting this error, and that error is coming because of this line we added. Okay, here, so we added the single phase transport model. Okay, so what is needed, I think this few lines is needed. like we add this transport model, but we didn't add the library of the transport models. Okay, so I think that is the failing. So let me set this options files. So let me include this library as well here. Okay, and now let's recompile it. Okay, so sometime it's happened, everything went fine, but we not able to find out. So but it's, I just remember that because of this maybe few lines, because we added the include file, but we didn't added these libraries. Okay, because of that only that is failing. Now it's compiled properly. So now let's go back to the create field.h file and also initiate all these entries whatever we commented previously, and again let's compile it. So we able to set the create field files. So let's go back here. So what we did, we able to set up to here. Now let's uncomment few more part. Okay, so let's say up to here. So Ico multi-region form, so that we have to modify. So go to the fluid area, compressible multi-region form. Okay, in case of that, rename to Ico. Okay, Ico multi-region form. Come back here. Okay, in case of here, it's supposed to be the Ico multi-region form. Okay, so that is what needed up to here. So Ico multi-region form, that is fine, that is needed. So we activated that Ico multi-region form. Fine. Now go back here. Then solid region diffusion numbers .h file. Just check that file. Solid region diffusion number .h file. So solid region diffusion number .h file. So let's look at that. Okay, so in this there is so many entries, like they're reading the kappa, cp and all these things. So that is not at all needed. Okay, so up to this part I think not required. Okay, so up to this part not required, correct. So let me comment this area. Okay, so this area not required. Okay, so this is fine. For each solid zone it try to check. Okay, and here what we required is an I. Fine. So for solid I, now we don't have a row cp straight away. So in the similar line, the way we have this similar line, we supposed to have a row. Okay, so we require cp of s. Okay, solid cp. Then we required row s. Okay, this is no more required. Then we required, in case of kappa, okay, we required ks. That's it. So with this we are set for these values. So all these things we are reading in the create solid files. Okay, so if we try to open the create, sorry, not mesh, try to open the create solid field file, we will have all that entry that is needed here. This. So all that entries whatever needed is here. Okay, so no worry. So we able to set this file, I think. Okay, so let's compile till that state. Okay, so now let's go to this area, Ico multi-region form. Okay, so we activated up to here. Set initial multi-zone delta t, it's already there, so we need not to change anything. Let's see. Okay, so it says that row fluid, no, not row fluid, from where it is asking for row fluid, multi current number, Ico multi-region current number .h file, Ico multi-region current number .h file. We didn't look at that file, so let's see that file as well. Ico multi-region current number .h file. Fine. So here we have a row fluid zone, that is I think fine, row fluid zone. Then why it's saying row fluid was not declared in the scope? Why row fluid is not declared in the scope? Because we already created this thing here. That is correct. Row of fluid is not declared in the scope. That is absolutely correct, because that is no more needed. So let me delete that part. Correct. Okay. So row is not declared. That is fine. Now it's a KS was not declared in the scope. What else it's saying? That init current number invalid initializing reference type blah blah blah. So where is that problem? We are here. Wait, zone. Okay, phi of fluid, correct. I don't see any error. This is all commented. Okay, scalar same way, fine. Then fluid regions, fine. So where it's saying on 12, line number 12, this comma is required anyway. This is also required. Let me clean it and compile it again. Another error is saying KS is missing, where solid may KS, maybe K is capital for create solid field. K capital, that's why K is supposed to be capital, fine. So now if you see, we are able to get that only one error. Solid diffusion number not declared in the scope. From where? First of all, let's clear this error, saying that Ico 39, and then on that we are calling the functions as Ico multi-region current number .h, invalid initializing reference of type volume scalar, void of, where is volume scalar? There is no any volume scalar here. Scalar for all. That is how exactly one can find it out. Let's see. Okay, let's open one by one. Fine. So that is fine. Now Ico multi-region current number Ico multi-region current number. This is the problem. Ico current number.h file. Row is missing, so let me change the row. Not required. Perfectly all right. Invalid initializing reference type, line number 12. Why it has an invalid initialization? It is a fluid, correct? Fluid zone, I think is fine. I didn't getting why that error is coming. Ico multi-region form 69. That is exactly it's saying that we are calling from line number 69 here, this in function in it. Okay, invalid initial reference of type volume scalar expression to type this. Okay, let's see. Ico current number scalar current number. Okay, because of this, because Ico current number, if you see, okay, here also we have a row everywhere, so I think that is the problem. We're supposed to switch off this row from this area, no more needed. This also no more needed. Okay, C file phi row. Now now what to do? We have to calculate this current number. Okay, and we have to calculate the current number without this phi. So I think this part is not needed. Row. Let's see. Fine, so we set with that. Okay, because row was here, so we don't require that row. Fine, so we are set this. Now check about this. Okay, so region solid diffusion number dot h file. First go there, region solid diffusion number dot h file. Region diffusion number. Okay, so now we have to check for solid diffusion number. These files we have to check. Okay, here, so solid diffusion number, this file supposed to be now modified. Okay, because now we don't have a volume scalar field as a row CP, we have a CP. Let's say that we have a row, comma, we required one more entry, that is, so what we have here, where here we are sending CPS, row S and KS. Okay, and that entry goes here, CPS, row S and KS. Okay, So we are considering this all the entries here. Fine, so we adapted that. Fine, now modified accordingly here as well. So all these entries we needed. Okay, so we needed all these entries. Fine, now let's try to change this thing. Okay, so scalar, fine. Okay, then we said that kappa to interpolate. Okay, so we have to interpolate kappa. So here we have a k. Here we say that interpolate rho star cp. So we interpolate cp star rho. Okay, we are set with this. Now mix runtime, that is fine. I think it's okay. So we set k rho cp. Okay, and try to interpolate it and check it. Let's see now. Solid diffusion number .h file has a problem. .h file 44. Solid region diffusion number .h file. Okay, .h file, yeah, correct. There's a problem because we have added additional comma. Number C 36 here, correct. We added this comma, all these typo errors. Okay, now just check either we able to correct it or not. I think it goes fine. So we are set with what up to this part. Now let's say look at this, set initial multi-region delta t. I think that will not create any problem as far as this thing is concerned. Fine, so we are set. Now let me initiate this. Okay, runtime. Okay, out of that create, fine, read pimple, fine, Ico, no problem. Now we are set with this multi-region. I think not issue. Then also let's check till here. Okay, fine. So up to this part, let's see. Unused variable, that is fine. Let on it going to be used. Perfect. So we are set up to here. Now let's look at this. So here we have a set old value, no problem. This, now look at the sol fluid part. Okay, so for that let me switch off whatever is not needed at present. So we try to clean the number of files that is not needed. Okay, pimple, let it be. So now we want the fluid solver, solve for fluid. Let's see. So solve for fluid, if we see anything is needed, let's see. Okay, so solve for fluid, okay, yeah, before solve for fluid and before the solve for fluid, what is needed, just check here. We have to set region fluid field. Okay, so that is very important. And then we read the multi control. So before we go towards solve fluid.h file, let's set this set region fluid set field dot h file. So if you look at that fluid, we want set region fluid dot h file. So look, in this particular file we are setting the each zonal property. That is the idea. Okay, so whatever is not needed, we have to get rid of that part. So what is needed in case of this, we require the single phase transport model as a thermo in compared to this thing. So for that, what we needed is something like this way. So create fluid, we are using this single phase transport. In case of the row thermo, we supposed to use single phase transport model, and from that we are adapting this thermo. Okay, the argument not needed. What else we required? If you look at these files, how many things we are creating? We are creating that many things. So that many things, whatever we want to read, that many part we have to be there inside of this particular area. Okay, so let me check it from this side. Okay, so let's see how much and how many things we needed. Okay, so this is the new things we're going to add up from this side. No argument required. So start with volume. Let's say this V fluid we needed, so definitely let it be here. Then V fluid, then we required the phi of a fluid, so let it be phi of a fluid. Okay, then P required, so P is a volume scalar field, so straight away copy from this area. So we required P and it goes as a P fluid. Okay, then T fluid is also a volume scalar field, so we required T, goes as a T fluid. Okay, U T fluid, that's fine. Okay, then we required K, so K is also a scalar field, so K of a fluid, fine. Then we required some phi we needed, fine. Then we required this all properties. Okay, and before that we required this turbulence characterizations as well. Like here we have compressible turbulence. In the similar line we supposed to have a incompressible turbulence, so let's copy this side here. Okay, in case of compressible, now we have an incompressible, so let's add up that incompressible turbulence part. In case of this, we require incompressible turbulence model turbulence 1. Okay, then P we adapted T as well. Then now we require this all these entries. So for that, what is this entry is a dimension scalars. So just check how we are reading the dimension scalars. That is not a constant scalar, this is simple dimension scalar. So let's best add up from here. So what we needed along with this, we required, let's say, dimension scalars. Okay, what scalar we required? Nu. Okay, and equal to Nu fluid, and then the zone. Okay, so that is one. Along with that, what else we needed? We required PR, then PRT. Okay, so we set with this PR PRT. Along with that, what else we needed? We needed these cells as a label. Okay, so let's set that as well. So that is nothing but the label and the one scalar. Okay, so what we needed? We needed label. What label we needed? We needed label equal to P cell, and but that label is as a constant, not supposed to change. So constant label equal to P reference cell equal to same value whatever we have here, and for the first fluid zone. Okay, in similar line we required scalar. Okay, so let's say scalar Okay, scalar of what? Cell value equal to this one and this thing. Okay, so that is all what we needed. Okay, so let's comment all the entries that is not going to be used here. So fine, we set with the set region fluid field, we set in the similar line we supposed to also set for a solid field as well. Okay, so let's check for solid field as well. So both the things we able to set at a time. Okay, along with that we supposed to set for a solid field as well. So let's go to the solid area, set zonal region solid field property. Okay, here FV mesh fine, solid thermo not required, so let get rid of this. But what we required some volume scalar field. Okay, let's say we required certain volume scalar field as a row, and that row is nothing but we are reading as a row of a field I. Okay, rows of field I in the similar line. Okay, so let's keep a tab. So we required volume scalar field as a row, then also we required volume scalar field as a CP, and that is we are reading from CPS. Then we required volume scalar field as a K, reading from KS. Then we require volume scalar field as a temperature, and we reading as a TS. Okay, so that is what we needed. All rest are commented part. So we are set with the create a set region solid field.h file. Okay, so that is what needed here. So we set with this. Now let me comment whatever not needed, means whatever we yet to set. So these two files we set, this two file we yet to set. So now let's compile it and have an idea. Okay, so reception failed, y unused, p fluid. Okay, it is in the store old fluid set.h file, so we have to store fluid set.h file in the fluid. Okay, so we have to modify this file. No more it is a row, it is a p fluid, and row I think not required, so we don't require this. We only require the store of a pressure, that's it. This is our unused variable, that is correct. Later on we are going to use it and we fix it. Okay, so we set with this old set because previously it is a different part, but now we have only row. Row is not there, only pressure store previous iteration required, that's it. Okay, so we are set with that. Now let's open this part. Okay, check any error is there. So we are reading the its properties. Okay, the similar line, let's read this as well. Okay, so all this variable going is unused, so it's just warning. When we start using in the code we will set. Now let's say solve for a fluid. Okay, so we start with solve for a fluid. Now if you look at the solve for a fluid area, okay, so let's check first solve for a fluid. So we are set with this, create field find. Okay, solve for a. Now let's fix one by one all the equations. Okay, so let's start with the u equations. So let's open first u equations. So if we look at the u equations, so it's based on the compressible environment. Okay, so let's now fix this u equation based on either pimple form or the piezo form. So let's fix with the based on pimple form. So, okay, so here whatever we needed, we just copy that area into our area. So this all the things not required, so I simply deleting that part. Okay, we don't want to activate the MRF, so let's comment that part. Okay, MRF no more needed, so let's comment that part. Whatever needed, we continue with that. Okay, FV option, let it be. Maybe it is useful to activate the FV options, so that is fine. Now also try to look at the this one CHT from CHT multi-region form. Let's also look at the solve for fluid. So if you look at the solve for fluid, in case of the piezo loop, they are using like this way. Okay, so we also try to add the similar line, because the piezo.correct sorry, it is piezo.correct is not available basically. Okay, so basically we want this in case of the piezo.correct, and let's comment this part. Okay, so that is what we required from this side, so we are set with that. Now let's do one by one. So let me also comment this one, only check for U equation either we are getting any error or not. Okay, so let's look at that part. Okay. So let's try to compile it and observe either we are getting any error here or not. Okay, so turbulent, this part is failing. Okay, so solid.h, yeah, solid.h is active. Okay, so go here, let me comment this part as well, later on we fix that. Okay, fine, so we have error at turbulent, this part is not available. Okay, and then pimple dot momentum predictor is not available. Okay, so in the U equation this pimple dot momentum predictor is not available, that is correct. We only have to work with momentum predictor. Okay, but this part is missing, so let's observe from the older file of U equation how they fix that. Okay, so it is nothing but turb dot this way. Okay, so we have to modify it by this style. So we have a, in case of this, that is correct because no more that part is available. Okay, so let's see any other error we have. Fine, so we are till now we are set with up to this part. Okay, so U equation is set, so let me close down all the things related to U equations. So we are set with the U equations. Okay, few things I activated, that is this FVIO options. Okay, because if you don't have FVIO options, then you not have able to take this FV option part in it. Okay, so I activated the FVIO options. Along with that, I also activated in the this sol.fluid file, in the create field I also added this part. Okay, fluid FV options, and when we activated this fluid FV options here, we also supposed to set that in the set region fluid property. So here also I added, so these few lines I added in all these files. Okay, to enable the FV option, this part. Okay, now let's go towards the pressure equation. So we are set with this. Okay, Now if you look at here, we only enable the U equation. So in the similar line, let's also activate the P equations from here and check for P equations. So P equations is based on the old style, so let's add up the P equation from, let's say, Ico form. Okay, and then we try to modify the P equation based on our requirement. Okay, so let's adapt to here P equations. Okay, so also try to check the P equation from the old file. Okay, so if you look at the P equation here, what it has couple of the things. Okay, based on this compressible part. So anyway, that is not needed for our part. Okay, exactly the same thing. So let's try to add up this equation from this area. Okay, here. So I am deleting everything and keeping our this equation. So maybe we have to change couple of the things here. Okay, so for that, let's open the P equation again. Look at the P equations. Okay, so we are using this based on U dot U equation and comma. Okay, so here we don't have a U equation and this thing, so let me change this. Okay, let's first figure it out. If we get the error, then we try to change, but maybe sometime we get the error because of that. Okay, so our P equation is on now. Okay, so let's see. So we are getting the same place this error because of that only. So we supposed to have this thing at both the locations. Okay, if we have that, now let's check, are we getting any error there? Okay, so this part is done, but the piezo dot correct non-orthogonal, that is not available. So piezo dot correct non-orthogonal is not available. So let's look at the read pimple control. So in this, what is the name we gave for non-orthogonal character? Okay, non-ortho character is this name. Okay, so let's try to fix based on that name. Okay, so we are here now, piezo correct non-orthogonal. To that we have a non-orthogonal character. Okay, and if we able to manage, let's see with the help of that. Okay, again we have a few error here, P final iter and all these things. Okay, so it is here. So we have to modify this portion by some different ways. So let's look at here how exactly they coded here. Okay, so non-ortho is non-orthogonal character. If, then it does its job. Okay, let's see for this part which one, while non-ortho character. Okay, they have this thing for init non-orthogonal character. Okay, and then inside of it they are solving for that. Okay, so this part we have to modify definitely. Okay, otherwise it's not going to work. So non-orthogonal pressure character, fine. P sol finer iter. So finer iter is, we don't have any concept of finer iter here. Look, in this we don't have any finer iter. So in the similar line we have to modify that portion, there is no doubt about it. Okay, so let's try to do that. This portion we try to copy from this area. Okay, and we have to modify this portion based on that. So we take help from here. So non-orthogonal character, so we say non-orthogonal character as compared to that they are using this. So let's use the similar line, this portion, fine. Then scalar, this is the same thing what we have here. Okay, so non-orthogonal character, and then we have a scalar of this part, so that is exactly this portion we are set. Then we say p reference p cell. Okay, then when we say let it be this way, but solve we have to solve something like this way. So solve equation for pressure only, p equation solve, this is p set only. Okay, then piezo final not possible to incorporate, so this portion we have to copy from this area and have to fix in this zone. Okay, so this portion is set up to here. Then we have a, in case of p final orthogonal, we have a p equal to non-ortho up to here. Okay, at that point of time we are dealing with this, and then we are set for that. Let's see again, and then we do that, and then finally close volume. Okay, so let it be the way we have here, no worry. So up to here, let me fix that part. Okay, then we say for continuity error dot h file. Okay, so continuity error dot h file, in case of that, here we have a compressible continuity error dot h file. Okay, so we have to manage that part. Okay, in case of compressibility, we supposed to have a Ico compressibility error. So at present I am commenting this, because first let's compile this, then we modify this continuity error. Okay, so let's try to do that. Okay, few more error. We non-ortho was not declared in the scope. Non-ortho, non-init, non-ortho equal to this. Somewhere something is failing, where just check. Init, let's see, in it, fine, that is perfectly all right. Init non-ortho gonal less than non-ortho plus, so we modified it correctly. Init non-ortho, this non-ortho is less than equal to the character. Okay, that is one way, or straight away we write as a non-ortho, something like this way. We have a this, so non-ortho we read it in terms of non-ortho character. So let me check either it allow me to fix it or not. Okay, so non-ortho, Control G, let me try it again. So it says that non-ortho is missing, but why it's supposed to be non-ortho -1 outer character. Okay, outer character we have, okay, but we don't have this one, so maybe because of that only it's saying us. Let's see. So sometime we stuck with few errors. Okay, so but with the patience we have to clear that error, because programming when we do, we have to have a lots of patience. Okay, that is the way. So 1735 P17, it's saying something at that location. 17, okay, sorry, here saying it near about 17, here says that comma nothing that will affect. So let me do it some other way. Okay, so I say till the non-orthogonal is there, it's supposed to work. Before that, let's initialize it, init equal to this, and then first second, then we send init equal to this plus 1. Okay, so with the help of that we are set with non-ortho part, I think. Before that something is missing, it's saying. So before that something is missing, while, okay, that is correct here. Fine, so we able to set with that. Okay, so we adapted few things from the CHT multi-region form. Now let's fix this continuity, Ico continuity. So at present, if you look at the folder, we have a compressible continuity. So let's rename it in terms of Ico continuity. Ico continuity. Okay, and now let's open the Ico continuity part. So we have a Ico continuity error. Okay, so Ico continuity error is at present, let me delete this part as well. This is belong to the that one. Okay, so Ico continuity error, let me open that. Okay, but this continuity error is calculated based on the older style, but we want the current one, so we quickly look at based on the net from the Doxygen where exactly the continuity errors is calculated, and we simply copy that area. Okay, so let's say Doxygen. Okay, and inside the Doxygen, if we look at the Ico form, we have this continuity error.h file. So we have to modify this based on our requirements. So let's add up few things from that area. So let's look at the code. So these things we required. Okay, so it is available at which location? SRC, finite volume, CFD tools, and incompressible. In that part is available. So let's try to search for that. Okay, SRC, okay, then finite volume, CFD tool, SRC, finite volume, CFD tool, incompressible, and here we have a continuity error. Okay, so this portion we require to be copied from this area to our this area. Later on we modify it. Okay, so volume scalar 5 phi, no problem, we have that continuity. But look, here we have a continuity in terms of the array because we have multiple zone. Rest I think is fine. So here also it is a continuity. Global is locally defined, so no worry. So let's comment this portion from this area to this area. Okay, and we are think set for continuity, everything we have. Okay, so let's compile it. So continuity is set with this. So let's come back here in the P equations. So P equations, everything it seems to me is set. Okay, so P equation is set, U equation is set. In the solve we are set with P equation, U equations. Okay, now think about the T equations. So let's try to add up the T equations. Okay, for the T equations we try to copy first, let's say something like our u equations, and from that we try to add up the t equations. Okay, so let's first copy the, because no more we going to use the energy equation, so let's rename energy equation as a t eqn. Okay, so t eqn is now we have, so let's open the t equations. Okay, but t equation has so many this thermo and all this part. Okay, as compared to that, what we needed the t equation in terms of most simplified way. Okay, so what is the most simplified way? We require the t equation in terms of incompressible way. So let's try to figure it out from where we get that concept. So one thing is sure, that we straight away add up the scalar, this thing in the basic scalar transport form, and if you open the scalar transport form, this is we easily adapt. Okay, so that is take in mind. Then let's go to the heat transfer. Let's say as compared to Bossiness, let's look at the Bond form. It also have a E equation only. Okay, Bossiness. Okay, so Bossiness has a T equation, so let's look at that Bossiness Pimple form. So Bossiness Pimple form has a T equation. We try to add up this and try to modify based on our requirement. Okay, so this is the T equations. Okay, so Bossiness, based on the Bossiness we try to modify it. Okay, so first we required what volume kappa effective or alpha effective, whatever you say. Okay, so that is needed. So for that we straight away define here, because we need not to define this alpha t. Okay, so it's better without defining the alpha t, one can quickly create this volume scalar here itself. Okay, so let's say alpha effective, we try to define here itself. Alpha effective is straight away we try to use the way we want. Okay, so let's say alpha effective is the name, and then how we modifying, we are modifying in terms of turb.nu. okay, from the turb.nu divided by PR, and we also required the in alpha this one. Okay, nu t, so straight away we define here itself. So alpha turb nu t divided by PRT. So with the help of that we are set, so no more this thing is required. Okay, this is typo. So with the help of that we are set with the this thing. Then we have T equations, so alpha t Laplacian of this. Okay, no more we require the radiation or anything, so let's just delete that part. Then we required this T relax. This, let's say we are not using any this thing. Okay, then radiation not required. T relax. Okay, so it's T relax, and then we say for solve for T equations. Okay, I think that is the very simplified way one can fix the T equations. So let's activate the T equation and check for error, either we are getting any error here or not. So we are set up to here. Okay, thermo is that saying it's unused, that is fine. Okay, K of fluid, Nu of fluid we are not using anyway, no problem, but in the other route we are using. Okay, so we are set with the T equation, P equation, everything. So we are set with the, I think, the fluid side. So let's look at the again here. So we are set till fluid side. Okay, now set for solid side. So for the solid, let's open this solid fluid. So solid fluid we have to modify it based on our understanding and requirement. Okay, so solid fluid.h file, what we needed very simple way of looking at it. But one thing I am thinking to modify the anyway non-orthogonal character way. If you want to take the t equations, then we have to modify the t equation by different way. Okay, so what I am saying, if let's say there is non-orthogonal correction we have, okay, and we want to implement the non-orthogonal character here, we can use that as well. Okay, so that is possible. Okay, till this correct non-ortho. Okay, within that we can simplify it. So if you want, we can modify this portion. Okay, modify this portion till we have a this non-orthogonal character required. Okay, so what we can do, we can use this non-ortho, this option here. Okay, till non-ortho. Okay, and this part doesn't change anywhere. So from here we say non-ortho, and all these things goes inside, and later on we have a over. So as many time we have non-orthogonal character, that many time this particular equation going to be solved. Okay, so it will stabilize the t equation, nothing else. Okay. Yeah, this error is because of the we activated this portion. So let me comment this part and then again try to compile it and check. So later on, whatever we are not using, we try to comment out. Okay, all the portions. So okay, fine. So now, so we are set with that. Now let's look at this solve for a solid. Okay, so solve for a solid is also we supposed to change. Okay, solve for a solid in the similar line, the way we have a t equations. Okay, in this still what we are solving. Okay, in the similar line, one can add up the solve for a solid very quickly. Okay, so if you look at here, okay, that is better. We have this terminology non-orthogonal, or we use the while, anything is okay. So let's work it out that way only, that is better. Okay, so we have a non-ortho till all the non-orthogonal correction. Okay, it try to solve. So what we have here in the t equations, so let me open the t equation from again from the our CHT multi-region form solid and solve for this. If you see, we have a energy equation. So in case of that, we now have a simple t equations, but what is needed here, definitely we require rho star Cp, okay, comma of this thing. Along with that, we don't require this portion, it is just simply the diffusion equations, and here we require the k. Okay, and then we say relax for t equations and solve for t equations. Okay, anyway this option is not required, and this thing we do for as many time we have a non-orthogonal character, that many time we try to solve for that. Let's say so with the help of that, we are almost on the finishing line of the code development. So let's observe again. So we are set here. Okay, now few things. Momentum predictor is unused variable in read pimple control, then read pimple control, and character and non-orthogonal character all are unused variables. So let's look at that. Read pimple dictionary, we are reading what is unused. It says from line number 77, whatever is called line number 77, read pimple control. Okay, read pimple control we have, then read fluid multi-region pimple control. So I think read pimple control is redundant, it seemed to me. Let's see if it gives us error, then we again activate, otherwise stop it. Okay, so for this n outer character, it is part of that part. Okay, n outer character, so that is needed, so let it be available. So whatever is giving us the warning, we try to comment that portion from read pimple control. So what it says is that line number 10, 13 and 16 is not in use. Read but 10, 13, okay, and 16. So that many things is not needed from this area. So I copied this portion from the another part, so that is not needed, it's fine. Then okay, and final character, now know where we are using. Okay, warning unused variable in 99 line number here, this one. So no more we are using this final iter and all these things. So at present let's comment that portion as well. Okay, what else? It says that set region fluids.h file. So let's look at set region fluid.h file. Okay, from here it says that line number 3 no more in use. Okay, fine. Then line number 9, k none of the places at present we use. Okay, and nu at 13 we didn't use like that way. So later on, if required, we will activate it. Okay, fine. So wclean.all, let's see, compile it again, and if it's set, then we are set with the our solver development part for this multi-region form. Fine, so we are set with the solver development here. So we develop the code. Now let's do further modification in the code. So if we look at, so we ready with this Ico CHD multi-region form. Okay, and in this particular solver we try to look at the conjugate heat transfer type of the scenario. So we set with the solver, but that is not enough, because when we work with the solver like multi-zonal type of the thing, so we require the interface boundary conditions, and we have to set that interface boundary condition. So here I already gave you the required set boundary conditions. Okay, so that is available in the derived FV patch field, and here we have two options, either solid wall heat flux or the solid wall mixed temperature coupled type of boundary condition. So from where we supposed to adapt this class of boundary conditions, so I will show you from where I adapted that conditions. So for that we have to go to the release version of OpenFOAM in the SRC folder. Okay, so first identify from where to find out that. So for that, go to the previous tutorials. So tutorial, heat transfer, CHD multi-region, any one tutorial pickup, go to the system and any of this thing, let's say top air, here you have a change directory type of the dict file is available, and from here try to look at for the temperature, because the mix condition we have to apply for the temperature only. So here they are using something like turbulent temperature coupled mixed type of boundary conditions. Okay, so let's copy this area. Okay, and first let's go to the that folder. So cd OpenFOAM. So we have to go to the src folder. Okay, and we have to search where exactly that things is coded. So if we search, we will come to know that it is coded inside the turbulent model, compressible, turbulent fluid thermo. Inside that there is a derived patch. So let's go to that area, because it is based on the compressible model, so that's why it is under the compressible environment only, but we cannot use that compressible form of wall treatment or wall boundary condition. So we have to derive that condition or write our own incompressible type of the conditions. So if you look at here you have a couple of options. So whatever I gave you, that is developed based on this external coupled temperature mix and external wall heat flux temperature. So based on this, that both the conditions, whatever you are seeing here, it is developed. Okay, so that conditions I already developed and gave you here. So if you look at the let's say wall heat flux conditions, so let's go to inside of it. Okay, so wall heat flux conditions, so that is nothing but the fixed heat flux we have to specify. Okay, so for that we know that the if we want to fix the wall heat flux, okay, as a interface condition, so wall heat flux we can fix in terms of the gradient. So Q is the gradient divided by K. Okay, K is the thermal conductivity. So nothing but we are using the let's say Fourier's law of conduction. So Q equal to K A dt dn, and dt dn is the gradients, and Q dot we are using. So Q dot is Q and divided by K. So from where we are getting these conditions to be set. Okay, so and when we set this condition, so during the compilation itself we have to direct use this inside the Mac folder. So I did the necessary change as well. So in the file I also incorporated these two lines. So in the previous case we don't have this two line. Okay, so later on I incorporate this two line. Okay, and this two line we didn't construct in terms of the library, because we want to incorporate this as in, we don't want to link as a dynamically linkable boundary conditions, because it's the part of the code. So we supposed to incorporate that condition within the code itself. Okay, so that is the idea. So that's why we try to coded that library, sorry, that particular both the class of boundary condition here, and in the Mac folder when we compile in Ico CHT multi-region form, it is available itself. Okay, so let's try to compile that thing. Okay, so wclean.all, okay, wmac. So when we do the wmac, look at the beginning it try to also source this file as well for the creation of Ico, this Ico CHT multi-region form. Okay, so that is what you will see, the little bit change in the solver. Anyway, I'm going to give you this solver. So but I suggest you first start with developing at least core Ico CHT multi-region form, and then straight away add up this class of boundary conditions. Okay, so CHT multi-region form is ready to go at present. Okay, so now idea is that we have to simulate that CHT multi-region form. So for that we require the proper test case. Okay, so I have a one test case, so we try to add up the test case and go ahead and finish the task. Okay, so how to proceed, let's see. For that let's go to the area. Okay, so I am closing that part, new tab, go to the area of test case. Okay, so here is the test case, and here I gave the test case information. So let's look at, go to the readme file. So in this we have a two zone, one is the fluid zone, another is the solid zone. Okay, and for that, so it is almost like a multi-region form only, but in case of the multi-region we work with the compressible class of the solver. Here we going to work with the incompressible, what we develop, that solver we going to use it. Okay, so let's go to this area first. Okay, so let me open this here OF 3.0x. okay, so we are at that locations. Okay, and let's first type all clean. Okay, so we try to clean the case. Now let's try to establish the case step by step. So first is the block mesh. Okay, so if we after block mesh, if you see the paraform, we will see what exactly the block mesh has. Okay, so that is the block mesh we have. Okay, so and let's say, do we have any zone or anything? We at present we don't have anything. Okay, so this is the block mesh, and that is one zone we constructed, and it is we are working in the 2D. So we now try to create a 2 zone out of it. That is the idea. Okay, so we have a zone, then we say set make cell dot set file. So for that I already gave that make cell set file, and we are constructing the box. Okay, and adding this box into the solid name, and then we say invert the fluid. Okay, so like that way, with the help of this make cell set dot set bash file, we are able to construct the 2 zone out of this 1 zone. That is the idea. Okay, so let's use that utility. Okay, so readme file, so let's use this utility. Okay, so it allows us to construct the 2 zone. Okay, out of it. So paraform. Okay, later on we try to read, then set to sets to zones, no flip flap. So we try to construct the 2 zones. So look, the sets 2 is found and added to the set fluid zones. Okay, so that is now added in the fluid zone. So let's see, can be able to see both the zones here. So zones, if you look at, we have these 2 zones. Okay, so let me only look at the fluid zone. Okay, and then we have a solid zone. So like that way we separate out our one block into 2 part. Okay, with the help of that 2 command. So now we are set with that. Now let's split mesh region cell to overwrite. Okay, so now we are splitting the mesh. Okay, first we constructed the, now we split the mesh. So that command is very essential. So even though you, let's say you generate the mesh inside ICM or any external mesher where you have 2 volume, after that up to this it's fine. Either you generate the mesh inside the with the help of block mesh, any class of the mesher, but when the 2 multiple zone mesh you add up in the OpenFOAM, the split mesh zone command you must run. So why it is important, let's again clean the case. Okay, so after that we will I will try to explain why it is important. So let me first reach up to here. Okay, so we able to split the zone. Now if you look at here, constant folder polymesh. Okay, in the constant folder we don't have a multiple zone folder. Same way in the 0th folder we don't have a multiple zone folder. Okay, so we require the 2 zone. Okay, because it is the multi-zone solver, so we require the mesh also for 2 different zones. So if you remember from our advanced training, you will understand this part. So as a split mesh zone, if you do, after that if you check everywhere, look here, based on that zone, so this is zonal property. If you see here, we say fluid is a fluid and solid is a solid. It's not necessary you give the same name. Whatever the name you require you can give. Let's say you add up the mesh from the ICM, and in ICM you gave the different name to the fluid volume and the solid volume. Accordingly you have to give the name here. Okay, so that is the one thing. So after running that command, you will see that constant folder also have this 2 part. Okay, along with that 0 folder also have a 2 part. Okay, so that is needed from here. Okay, so, and then we say now we have to establish the boundary condition. So when we want to establish the boundary condition, what is needed, we require the change directory command to establish the boundary condition. So change directory command for a fluid. So what exactly is needed is from the system folder. If you see inside the fluid, I already have this change directory 1 file. Okay, so it try to establish the boundary condition. So we know that for this multi-zone type of the things, we have to rely on this change directory type of the utility that will fix the boundary condition at a time. Okay, why we have to run this? Because of following reason. Let me again clean the case. Okay, if you clean the case, okay, and then let me run till that utility. before this change directory. So with the help of that, we able to split the zone. So if you go to the 0th folder, you will see the multiple zone, but if you see here, till we not able to establish the proper boundary conditions. Okay, so that is why we needed that. So but after the change this command, we will have a proper boundary condition set for each and every entry. That is the idea. Okay, so for that purpose, we have to require this condition. Okay, in the similar line, we have to run for a solid as well. Okay, so we set with the boundary condition environment here. Okay, then we have to copy the certain properties that is needed from the basic constant folder to the respective folder. So here, if we see, we don't have any property. Okay, but when we work with the multiple zone, definitely the property is also going to read from the fluid zone only. Okay, and multiple fluid zones, so individual zones supposed to have. So for that, this two property we required in the fluid zone. One is the transport property, turbulent property, and the transport property for solid. So let's copy that appropriately, and if you require, you can change the property. So here, transport property, whatever we have, later on if you want, you can change the property as well. Okay, so that is what we are fixing here. So this is dummy file for solid. Okay, it is not needed. Okay, for turbulent, because we are not reading any transport property. So let me also delete this file and check either it's working fine or not. So later on, after that, so we copied this. I think this is not required, so let me comment that, and then let's try to run the case. So it's working. Okay, so what we did, we developed the solver. Okay, but this solver is going to work in the incompressible environment. Okay, so you need not to worry about compressibility part and everything. Okay, so the solver is running fine. So let's look at the its data. So when we want to do the post processing of this, okay, so what is needed, it is a multi-zonal problem. Okay, so let me open the new terminal. So we already have this thing, but we cannot straight away open this and able to do the post processing. For that, we have to use this command paratouch OF 3.0 paratouch. So after that, you will see this fluid and .openFOAM file is constructed. Now straight away use the para view, okay, to look at how exactly the simulation is look like. So try straight away go here, apply both the things. Okay, so one fluid and solid. So go to the fluid, go to the last part, open temperature, this thing. Same way here also open everything. Okay, so in the fluid part, let's look at the velocity. So this is how the velocity is built up, because this is the interface. Okay, and on this side we have a, let's say, temperature. Okay, so here this is velocity, this is temperature. Okay, now let's try to look at the temperature from fluid side as well. So this is how the temperature distribution is appear at the interface. Okay, so this is the temperature distribution at the interface. Now let's try to look at the filtering line Y. Okay, light. So at the fluid part, okay, how the temperature is vary, that is what you able to see from here. Okay, this is the temperature distribution at the fluid side. Okay, now let's look at the temperature distribution inside the this as well. Okay, so here not required. This is how the temperature variation we will see inside the solid. Okay, at the interface we have a 300 degree, 300 Kelvin, and after that away from the interface it is increasing to 309.5. okay, but if you see here for this thing, okay, so at the interface we have a 300 and away from this we have a 400. So that is how exactly the temperature variation is appearing inside of the this multi-zonal case test case. Okay, so we yet to converge, okay, fully. I think it's almost converged. Yeah, it's almost converged. So it's work pretty nicely, and for this you need not to go for compressible class of environment. It pretty good working in the incompressible domain. Okay, so what we learned with this session, we okay, let me delete this part because not needed. Okay, so what we learned is we established the solver, that is incompressible multi-region based solver, and we adapted the CHT multi-region form, but CHT multi-region form is based on, let's say, incompressible environment. So we converted in, sorry, compressible environment. So we converted that solver in terms of incompressible environment by step modifications. Okay, and then we try to run the case. Yeah, and it's working very fine. Okay, so here we stop for this particular test case.